Okay, so I'd like to take a look at problem 5 from the first exam. So this problem has us computing 3 different limits. So the first limit is the limit as x approaches 3 of x squared minus 9 divided by x squared minus 2x minus 3. So the first thing to check is this function continuous? Can we just plug in x equals 3? You'll see that if we do that, the numerator is 3 squared minus 9, which is 9 minus 9, or 0. The denominator is 9 minus 6 minus 3, which is 9 minus 9, so that also gives us 0. So we can't just plug in x equals 3 because the limit of the denominator is 0. But since there's also a 0 in the numerator, we might hope there's some cancellation, which lets us simplify things. So if we factor the numerator and denominator, we get x plus 3 times x minus 3 divided by x minus 3 times x plus 1. And if you cancel the x minus 3's, we see this is the limit as x approaches 3, x plus 3 over x plus 1. And now that we've canceled the terms that were going to 0, you can see that this is a continuous function, so we can just plug in x equals 3 to evaluate the limit, and get 6 divided by 4, or 3 halves. Okay, so now for part B, we have the limit as x goes to infinity, x to the 6th over x to the 5th plus 7. So in this problem, we see that the power in the numerator is higher than the power in the denominator. So that means that the numerator should be growing much faster than the denominator. So that means as x goes to infinity, this fraction should also be approaching infinity. So we expect that the limit is infinity, or you could say the limit does not exist. So to verify that, we're going to do a trick where we divide everything by x to the power 5. So there are other ways to approach this, but I think this is the easiest one to understand. So when we divide everything by x to the power 5, we get the limit as x goes to infinity of x over 1 plus 7 over x to the power 5. And now we can clearly see that the limit as x goes to infinity of the denominator is equal to 1, but the limit as x goes to infinity of the numerator is infinity. So we have something which looks like infinity over 1, which means that this thing is approaching infinity. Another way of thinking about this is the denominator just keeps getting bigger and bigger, the numerator just keeps getting bigger and bigger while the denominator just approaches 1. So that means the entire fraction just keeps getting bigger and bigger and bigger. Okay, so the last one was really tricky for people. I think there were only 1 or 2 who got this correct. So many of you correctly recognized that sine of 1 over x as x goes to 0 is an oscillating function. And rapidly oscillating, and as limit as x goes to 0 of that function actually doesn't exist because it's just oscillating way too fast. But it's not just sine 1 over x, we also have this x out front, and as x goes to 0, then of course this factor out front is also going to 0. So that means that we're multiplying this sine term by something which is approaching 0. And the important thing to notice is that sine of 1 over x, even though it's rapidly oscillating, it's always bounded. So negative 1 is always less than or equal to sine 1 over x is always less than or equal to 1. So since x goes to 0, and sine of 1 over x is bounded, that means that we have 0 times some number between -1 and 1, or something really close to 0 times something between -1 and 1, and as that something gets even closer and closer to 0, the entire thing will get closer and closer to 0. So that means that the limit is equal to 0. And to maybe give you more intuition about what's going on, let's look at the graph of this function. So if we plot this function, then it is oscillating very rapidly, but the size of the oscillations gets smaller as we approach 0 because this number that we're multiplying out front is getting closer to 0. So it's like a sine function with an amplitude that's getting smaller and smaller. And so the function ends up looking something like this, and because it's going to 0 here, that's why the limit is equal to 0.